and go from current slide. That's not the slide I wanted. Let's clear that was what we did last time. Okay. All right. Just a couple things first. Let me do a quick count here. None of the three of you are Lawson students, are you? You're all transients, right? Okay. I can't recall if anyone in this class is actually a Lawson student. I'm thinking not. So I'm going to leave off the first announcement. It has to do with the Lawson Math Club, Math Team. Since y'all won't be here in the fall, that won't be any difference to you. The second announcement, though, I guess pertains to you as well. I have mixed feelings about doing it because it's a company. I really don't feel like our job is to be promoting companies over other companies. And I don't know who their competitors are or anything else. But I know why they ask us to do it. Our Career Services Office is, of course, trying to line up students with jobs. Okay, that's the main thing they do. And this is a company that is really close to what we do here. It's STEM jobs. STEM standing for Science, Technology, Engineering, and Math. So this is a company that focuses on this. So they're trying to get us to do it. They come up with this new tool to connect classrooms to careers, they say. And at the top it says the STEM type navigator allows students to match their interests to opportunities after high school. And I think this is not the level we should be doing this. But the first sentence, and this company obviously is out of Pittsburgh, I believe, in an effort to connect students to opportunities from post-secondary institutions, employers, and the military, STEM Jobs has launched this STEM type navigator. So again, it sounds like it's a little lower level than what y'all probably are. But if you can use it and if it comes in handy, use it. So I'm not going to read the whole thing to you. If you're interested, here it is. You're welcome to take a look at it. And even if you want to take it home with you, fine, then I can announce it anyway or to other classes. But I think I've hit just about everybody. So you're welcome to take it if you'd like to. Okay. Let me also say this. I meant to say it in the first class, and I forgot to say it because I kept waiting for someone to show up to talk with. And then when it was already 6-8 minutes after, I said, let me go and get started. So I got started without this. This class, I have had uno, research paper turned in. This is basically the last month of the summer term, okay? This is it, folks, so please try to get moving on your research paper. Now, I'm still missing one test from test one. Thank you for the rest of you getting those in. The guy I talked with yesterday, and he said he had been hospitalized last week. His wife couldn't get it to me, but he said he was almost through with it. So as soon as I get it from him, I couldn't understand whether he was going to bring it by or email it to me, but I'll keep checking to see. As soon as I get that one in, I can return your first test to you. And he had a question, and Evan did also this morning, about the second chapter test. We're pretty close. Depending on how far we get today, we may have it today, but I think we're far enough out that we got this section to finish and next section, which we're not going to do the full section, but I'll just talk a little bit about that. Yuck. And then, so maybe we will be ready for it today. I've got it printed out, I think. I'm pretty sure it's printed. And if I give it to you today, then I'll try to get him his copy as well. Okay, any questions on anything so far? All right, last time we were talking about elementary matrices. Okay, can anyone refresh me on what an elementary matrix is? You aren't here, so any clue?
It's in row echelon form with one change.
Right. Exactly. Change from what, though? Where do you start?
You're going to do one of the three criteria.
Yeah, one of the three steps, and only one of them. But what do you do it on? What do you begin with?
Besides row echelon?
Yeah, to get it in, to do that one step in row echelon form. One step only. What do you operate on it with? You start with the identity matrix, exactly. Okay? Of course, identity matrix has to be square. Okay? So you start with the appropriately sized identity matrix and do one operation. One of those three operations. What are the three operations? Remind me.
Flip the row.
Yeah, exchange two rows. Multiply one row by a constant, non-zero number, which is also equivalent to dividing. If you're multiplying by 1/2, say it's the same as dividing by 2. Or add a multiple of one row to another. Yeah, those three, and those will produce our a single one of those to an identity matrix will form what we call an elementary matrix. Okay, and what the elementary matrix does for you is if you multiply a given matrix by the appropriately sized elementary matrix, okay, with one step done, that's equivalent to doing that one step to the original matrix. Okay, that's what it does for you. Well, the question might be, why don't you just do that step to the matrix? And that is a reasonable question because it's easier to do that one step to the matrix than it is to multiply the E matrix by that matrix. But it's easy to program matrix multiplication. Well, I say easy. You have to, how do I say this? When you're doing row reduction, you're making choices all the time. And to program a computer to make choices, computers are really stupid. I mean, artificial intelligence, all like this. You still have to program them. You have to tell it what to do. And they're getting much better with this. But it's so easy to program, say, matrix multiplication. It's the same thing every time, And if you just throw in the elementary matrix to do what you want it to do, then the computer can do the longer thing really quickly, and it doesn't have to think about it so much. Okay. Now, last time we started with the matrix. Okay, on page 76, chapter 2, matrices, 2.4 elementary matrices, and we started with in the example 3, top of page 76. We started with this matrix, A. Whoa. 0, 1, 3, 5, 1, negative 3, 0, 2, and 2, negative 6, 2, 0. Okay, we started with that matrix. Okay? Now, if we want to do this, as James was saying, in a row echelon form, what would be your first step? Reverse the top two, you swip the top two rows because you want the one in the upper left. Well, the elementary matrix that does that to you, we're going to call E1. Just what size will this need to be? Because A is a rectangular matrix, so a 3 by 4. So what size does your elementary matrix need to be? 3 by 3, okay? Now, and by the way, this is important. You always multiply the elementary matrix by the matrix. So therefore, it's 3 by 3 by 3 by 4 to give you a 3 by 4. You don't change the size of the end one, of the last one. So you always multiply on the left by your elementary matrix, even though I'm writing it on the right like they did in the book. And what elementary matrix would exchange those 2 rows for you? The elementary matrix that exchanges those 2 rows in the 3 by 3 identity. And what would that be? Zero, 1, 0. 1, 0, 0, 0, 0, 1. See, that's the elementary matrix. You started with an identity matrix, did one elementary row operation, which was exchange the top 2 rows. That's what you're wanting to happen here, so that's what you multiply on the left, A by, to get that to happen. Now, we're not going to do it. I mean, we'll just write it down because we did it last time. So your next step here would be 1, negative 3, 0, 2. And again, it's so easy to do. Why mess with the elementary matrix? Well, you're going to see in a minute. 2, negative 6, 2, 0. Okay. Now, what did we want to happen next? Trying to move, make this into row echelon form. Will be your next step.
The 2 on the far left.
You want that to become 0? How do we make it happen?
Multiply row 1 by negative 2.
Add it to row 3. So row 3 minus 2 row 1, right? So what elementary matrix, and we'll call this E2 just to have a, so it's different, would do the same thing as what we just said. What elementary matrix would E2 need to be that when we multiply it on the left by that to make the same thing happen?
We can multiply the top row by negative
2 and add it to the third. Okay? So we wouldn't do anything to the top row, 1, 0, 0, and we're not doing anything to the second row, 0, 1, 0, but the new third row would have been negative 2, 0, 1. Perfect. That's the elementary matrix that would do the same thing. Multiply that over here. That's the same as doing the row operation we just said. Okay? It will do it. And we did it last time. Okay? And in doing it, we got to this form. 1, negative 3, 0, 2. That stayed the same. 0, 1, 3, 5, that stayed the same, and the new third row was 0, 0, 1, negative 2. Okay. Now, we need, what's the next thing we wanted to do here? To get this in, I don't remember. This is row echelon, okay? Because you can do backs up as well. You don't know what that third column is. That fourth column. That fourth column was really a the equals, things on the equal side, or a augmented matrix and stuff like this. Yeah, you could back substitute right now. You say whatever this represented, Z is equal to negative 2, and then back up. But we don't know that's what it is. It was just a matrix to begin with. Okay? Now, no, I'm sorry. I skipped something. I was thinking, where are they going with this? I missed one. When we did that last step up there, this came out to be it snuck up on me. 2, negative 4. Okay, when we did that other, again, this is what we had left over last time. This is where we're starting this time. What do we want to do? This isn't in row echelon form. Close, but no cigars. Divide the last row by 2. So what elementary matrix would do that for us? We'll call it E3.
Row 1 and row 2 stays the same.
Okay, 1, 0, 0, and 0, 1, 0. That's a 2 down there, yeah. 2, negative 4. What would it be?
We're dividing by 2.
Dividing by 2.
It'll be negative 1.
No, 0, 0, 1/2. Perfect. Okay. We didn't get to do that last time, okay? And if we multiply this by that, and we can do it. We can move this over here and multiply by it. You'll find that that becomes a 1, that becomes negative 2. Then we're in row echelon form. Not reduced row echelon form, row echelon form. Okay? That's what we want for now. Okay? So, that first matrix there, and I think I was supposed to do this. I think we did it before. If you were to multiply this, I'm going to pretend it's over here now. 1, 0, 0, 0, 1, 0, 0, 0, 1/2. And let's actually multiply those and get the result over here. Okay, just so you see this indeed works. This would be so that's a 1 there. Next entry. This is a 3 by 3 by 3 by 4. It's going to give us a 3 by 4. So maybe I should fill in the blanks. Okay, 3 by 4. So the 1, 2 entry would give us a, whoops. Okay, just a negative 3. See how it reproduces itself? The 3, 2, 1, 2, entry, 1, 3 entry would be, yeah, that's 0. Again, reproducing that first row. And the 1, 4 entry. It's a 2, by the way. 2. Okay, 2. And if you go to the 2, 1 entry, 2 here, 1 here. Yeah, that reproduced itself. Ooh. All right. And then the 2, 2 entry. 2, 2. 1. Right? And 2, 3. 3. Sorry. And the 2, 4 entry. 5. So you see, you just reproduce those first 2 rows. No swap, no sweat. That's what this did for you. Now let's do the third row. 3, 1.
0, 0, 0.
Okay, nothing changed there. Okay. Actually, you took half a 0, by the way. But never mind, we won't go there. And then 3, 2.
0, 0, 0.
Okay? You took half of 0 again, didn't you? 0. And then 3, 3.
0, 0, 2.
1 half of 2. 1. Okay. That's exactly what we wanted it to do. Make that a 1, and it did. And 3, 4.
0, 0.
-2. You took half of that as well. That's why I said you took half of zeros before. You took half of everything in the row, and that's all you did. So sure enough, now we have it in row echelon form. That's the one I wrote down before by mistake because my eyes drifted too far south. Okay? Well, those 3 elementary matrices multiply by this one, but notice what they did. Okay? Now, I just sort of hate they wrote it the way they did. You took this one and multiplied it by that to get this, and then this one multiplied by that to get this, and then this one multiplied by that to get that. So what you did, you had A over here, multiplied it first by E1, next by E2, and next by E3. So you stacked them further and further out, always to the left, because that times this times this was this, and this times this was that, and this times that, just like I wrote here, finally produced that. So basically, the operations we just did were, and this we're going to call matrix B, so we could have said that B, matrix B, is E3 times E2 times E1 times A, right? You started with A, multiplied by E1 on the left first, and then that product that you got, we multiply by that gives you this as a result. You multiply by E2 on the left, so E1A, you multiply by E2 on the left, and that gave you this product, and you multiply this on the left, and that gave you B. Okay? Now, that's why we do elementary matrices, you might say. Why? It's so much harder to do than just doing row operations. Well, this maps out a very definite way to get from A to B without having to make decisions about row echelon form. All right. Now, some of you don't have books with you, or do all of you have access to a book? You do. All 3 of you. Okay. Well, I won't write it down. The definition of row equivalence, which we had way early, let A and B be both by M by N matrices. In this case, it was 3 by 4. Any M by N matrices. Matrix B is row equivalent to A when there exists a finite number of elementary matrices, E1, E2, E3, E4, up to E sub k, such that B is equal to EK times EK minus 1 times EK minus 2 times EK minus 3 down to E2 times E1 times A. If you can do them with all elementary matrices, as many as it takes, then those are called row equivalent. Okay? What's that?
What page are you on?
That's the bottom of page 76. See it? Okay. All right, moving to the top of 77. All right, here's a theorem. And y'all all have this, so I don't have to write it down. Elementary matrices are invertible. Well, let's see. Elementary matrices, number 1, have to be square because it came from identity matrices, which have to be square. Okay? And the identity matrix certainly is invertible, okay? It just reproduces itself. But if you do just an elementary row operation to an invertible matrix, it's still that. So yeah, the inverse of an elementary matrix, they are invertible. So if E is an elementary matrix, E to the minus 1, meaning the inverse of E, exists, but is also an elementary matrix. Okay, that's the key. Not only does it exist, but it also is an elementary matrix. Now, what we're going to do next is show what the prototype is for each of those. Okay? If this is E1, now it was the same E1 we used before. Okay? 0, 1, 0, 0, I'm sorry, 1, 0, 0. And 0, 0, 1. Okay. Now what would be its inverse? Goodness gracious, I can't write. E1 inverse. Okay? What would be its inverse? Well, you just swap the top 3 rows again of the same thing, so it's itself. Can't write. Okay. All right, now, I'm not sure I buy that. Do you buy it just hook, line, and sinker without any let's just see. What if you multiply 2 inverses times each other, what should you get? Multiply a matrix by its inverse, you should get the identity matrix. So let's see if we do. Let's see if we do. So 1, upper left. 0 next to it. 0 on the third. So far, so good. 0 there. Yeah, a 1 right where you'd expect it to be. I am convinced that will produce that. So when you exchange 2 rows, any 2 rows, in a of an identity matrix to give you that elementary matrix, its inverse is going to be the same swap again. You know, just exchange the same 2 rows. And Travis is here. We are moving toward complete attendance. I have a feeling we're not going to get everybody because one of the people who was absent this morning did show up, but the other one not looking promising. Okay, so, but 5 out of 7, even though you only see 4. One person talked with me yesterday. Okay, so that's what happens when you have swap 2 rows. The inverse is swapping the same 2 rows. Okay, it looks identical. We're talking about inverses of elementary matrices. Now, the second one that we had before was this one. 1, 0, 0, 0, 0, 0, 1, 0. I can't write today. Goodness gracious, this is aggravating. Okay, 0, 1, 0, and negative 2, 0, 1. Okay? What produced that elementary matrix? Which one of our 3 elementary row operations did that? Second? Okay, adding a multiple of one row to another row, right? That was an elementary row operation. That did it here, multiplying -2 times row 1, adding to row 3. Yep, that got you one. Okay. Now, what you reckon was the inverse there? Okay. What was E2 inverse? Anyone want to make a guess? I'll tell you, my first guess was multiplying either -1/2 or 1/2 to the top row and adding to the third. That didn't work, okay? But multiplying 2, top row by 2 and adding to the third, that does work. Now that seems bizarre. It really does to me. So I have to be convinced. And how do I convince myself? Multiply and see. So what happens here? First one. Yeah, so that gave me a 1, so that's okay. Next. That gave me a 0, I'm okay there. That gave me a 1, 0, 0. That's okay. Okay, I'm not worried about these first two. I'm pretty convinced they're going to work. Okay, do I have to continue? Is that third one? I'm not certain about that third one. So let's see what happens. The 3, 1. -2. That adds to 0, and I needed a 0 down there, so sure enough, that seemed like exactly the thing. Rather than multiply, whatever you multiply by one row and add to another row, just multiply the opposite to that same row and add it to the other same row, okay? So it's just changing the sign, okay? And let's continue and see if the others work too. 0. Yeah, that one worked. Yeah, that reproduced the identity matrix. All right, so if the elementary matrix is adding a multiple of some number to one row, adding it to another row, then to get the inverse, multiply the same first row by the opposite number. If it was plus before, make it minus. If it was minus before, make it plus, and add it to the same next row. That was pretty easy. So exchanging rows is just exchanging the same two rows to get the inverse. To get the adding a multiple of one row to another row, just add the opposite number multiple of the same row to its other row. So then this one. The third elementary matrix we had before was multiplying a row by a non-zero number. In this case, it was 1/2. Okay. Any of you want to hazard a guess about how you get the inverse of that matrix? And I'm going to suggest the top rows, 2 rows weren't changed before. Don't change them now. But we got to do something to the third row. What you reckon that might be? Let's try multiplying by 2. Okay? This one was multiplying by the additive inverse of the number and adding. So how about multiply by the multiplicative inverse? Let's see if that works. I'm okay with the first 2 rows, so I'm not going to mess with those. I'm going to mess with the third row now. So the 3, 1 entry. Yep. Yep. Yes, yes, yes. That did it for me. Okay? So, and those are the only three elementary row operations we have. Exchanging two rows, just exchange the same two rows to get the inverse. Okay? Adding the multiple of one row to another row, add the opposite of that multiple to that same row, and it works. And multiplying a number, non-zero number by a row is multiply the reciprocal of that number by that same row. That's how you get your inverses of your elementary matrices. Okay? And those are invertible, and these will be, the inverses, of course, will be invertible as well. So, you have access to a book? Oh, okay, good. So, Theorem 214, middle of page 77, a square matrix A is invertible if and only if, this is one of these that is a requirement now, if and only if it can be written as the product of elementary matrices. A square matrix A is invertible if and only if it can be written as a product of elementary matrices. Okay? Okay. There is a proof here. I'm really toying with the idea of whether I want to actually do it, and I guess we probably should. So the given here is a square matrix is invertible. Okay? With a square matrix, and by the way, square matrix A, invertible. It has to be square now. Before we were dealing with rectangular matrices. Now square. So let's say A is invertible. Okay. Now, if you go back a couple of theorems ago, 211, which was in section 2.3, I think. Yep, there's 211 on page 70. If A is an invertible matrix, then the system of linear equations blah has a unique solution. Yeah. Well, that didn't really tell us a lot, did it? Okay. This is a sort of a weird proof, and but if A is invertible, that means there's some finite number of elementary matrices, think elementary row operations, to get it to become the I matrix, right? If it's invertible and you do those operations, you're going to wind up, if it's a square matrix to begin with, you're going to come up with an identity matrix. Okay? So, if that's invertible, that means you can do A and multiply by E1, E2, E3, dot, 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 all the way back to E sub, say, K. Okay? And you can produce, if you take enough of those, ultimately you're going to get an I matrix of the appropriate size. N by N I matrix, right? Now, what we're going to do now is multiply by the inverse of each of these matrices. So, what I'm going to do is multiply this by E sub K inverse, right? I wish I'd left more room. Hold on. It helps to plan ahead. I didn't. Okay. Let's start over here. here you had matrix A. It's invertible, so you can multiply by some sequence of elementary matrices. You got to be able to do it at some point to produce the identity matrix, right? Now I left it way over there, and here's why. Because I can multiply this by E sub k inverse, multiply this by E sub k inverse, which is an elementary matrix, right? Okay? And then multiply, and since those two produce I, you can then multiply E sub k minus 1. And that will produce I here. So multiply this by E k minus 1. And then do it by E k minus 2. And it's going to wipe out that one and form another I here. E sub k minus 2. And then we'll dot this along the way until we get down to E sub 3 inverse. And that will produce I. And then E sub 2 inverse, and that will produce an I. I can't write. Okay. And finally an E sub 1 inverse, and that will produce an I. And we're back to A again. That's all we've got left is A, because all those paired up to be I's. And what do we have here? E sub 1 inverse, E sub 2 inverse, E sub 3 inverse, dot, 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 E sub k minus 2 inverse, E sub k minus 1 inverse, E sub k inverse. I forgot to put my inverses on all these. I did them, some of them. Okay? Times I. Okay? But guess what? I times all this combination of things that produces this combination of things. So forget about I. Okay? Okay? Leave it off. And these are all, they're inverses of elementary matrices, but they're themselves elementary matrices. So there, you have the product A. Any invertible matrix A can be written as a product of some finite number of elementary matrices. Done. Okay? All right. That's probably more than you wanted to see, but we did it. So let's move on. Any questions so far? All right. Let me reiterate something, because Travis wasn't in when I said it earlier. I think all the rest of you were here. Just reminders. Research papers, okay, due before the end of the month. So we're on the last month now, okay? So please get those done. Your first test, all of you have turned in except one person, and he's not here, but he told me yesterday he almost has it finished. He was just asking me how the best way to get it to me, email or bring it by in person. I said, it doesn't matter. So he said he'd try to get it to me soon. He was, I think he said, hospitalized last week for something, so he just couldn't get it done any sooner. So he's going to try to do it. And the second test, I'll either pass out today or Thursday. I have it ready. If we get far enough along today, I'm going to give it to you today. Okay. Now, example 4 is going to do what we just proved. It says, find a sequence of elementary matrices whose product is the non-singular matrix. It's another word for non-singular. Another word for non-singular. Invertible. If it's invertible, it's non-singular. If it's singular, it's not invertible. Okay? Sort of two negatives of each other. Okay. So here is A is equal to this matrix, -1, -2, 3, 8. Now, most matrices you can't do this, but this one you can. You can tell me with a very short calculation whether that's non-singular or not. Do you remember how? It works on any 2x2 matrix.
Multiply the cross product.
Yes, exactly. That's called taking a determinant. Okay? And for a 2x2, it's really easy. So it's down the main diagonal. What does that give you? -8. And then when you go to the anti-diagonal, the other diagonal, you subtract that product. And what's that product? -6. So you subtract it, it becomes a +6. -8 plus 6 is not 0. Doesn't matter what it is, as long as it's not 0. If it's not 0, it's invertible. Guaranteed. And that is invertible. Non-singular. Okay? So, we need to find a series, sequence, whatever you want to call it, of elementary matrices that you could say that product of those elementary matrices are going to make the matrix A. Okay? Now, I'll admit to you, this is a bit tedious. Okay? It's easy, but it's tedious. Okay? You ask yourself, what would be the first thing you do to row reduce that? Second? Yeah, you want that to be a +1. How do you make that happen? Okay, multiply the top row by -1. Now, what's the elementary matrix that does that? -1, 0, 0, 1. What is the inverse matrix of that elementary matrix? I can't write. That makes that happen. Yes, it's the same thing. -1, 0, 0, 1. Okay. Now, if you're not certain, multiply and say it's real easy, especially with 2x2. Be a 1, 0, that's a 1, 0, 0, that's a 0, 0, 0, that's a 0, 0, 1. Yeah, that works. That is your inverse of that. Okay? Hang on to that. Okay? Now, and by the way, that's going to make A become what? Help me. 1, 2, 3, 8. So what's your next step?
Row 2 minus 3 times row 1.
Say that? Yeah, multiply the top row by -3 and add to the third. Okay? So what elementary matrix is going to do that?
-1.
1, 0,
-3.
-3, 1. Okay. Now, what's the inverse of that elementary matrix? 1, 0 stays the same. What do you say? 3, 1. Perfect. Okay, there's your E2 inverse. Okay, what would this become then? 1, 2, 0, 2. Okay, and what's the next thing you want to happen?
Divide row 2 by 2.
Okay, we want to divide that by 2. That will give you 1, 2, 0, 1. And what elementary matrix will make that happen?
1, 0, 0,
Okay. Goodness gracious. I'm getting really airheaded now. I don't know why. Earlier this morning, well, my first class when I was in here all by myself, just got so congested. I think it's called the molds and mildews in the air, but whatever. Okay, what is going to be your E3 inverse? 1, 0, 0, 2. Perfect. Okay. And okay, this time we do need another step because we need to make this an identity matrix, remember? So what's your last step?
Row 1 minus 2 times row 1.
Okay. Row 3 minus 2 times row 2. Is that what you said?
Row 2 minus 2 times row 1. Or row 1 minus 2 times row 2, sorry.
Okay.
Negative 2 times the bottom row, added to the top.
Got it. Got it. Okay. So that would produce what?
1, 0.
Yeah. So that's going to get us there. And what did you say do again? Our E4 is going to be
1, negative 2, 0, 1.
0, 1. Perfect. And what would be the inverse of that one? 1, 2, 0, 1. All right. Okay. So we found the 4 steps it's going to take to make this into an I matrix. We found the 4 elementary matrices which would make those 4 steps happen. And we found the inverse matrices of those 4 elementary matrices that made that happen. Now, the question was, what is the product of what elementary matrices are going to make A? And what would be your conclusion? Okay? If you think about this, you started with A and you multiplied by E1, by E2, by E3, and by E4, right? So how would you get A back again? Multiply them in reverse order. E inverse 4, E inverse 3, E inverse 2, E inverse 1. So this would be, I just don't have enough room. I'm not really using those E1s anymore, right? These right here. I hope we did them all right. I believe we did. So let's erase these. And we're going to do what they told us to with I hope this won't be too messy. We do them in reverse order. 1, 2, 0, 1. 1, 0, 0, 2. 1, 0, 3, 1. And yuck. Yuck, I can't write. Minus 1, 0, 0, 1. Okay, those are written too close together, but I just ran out of room. All right. Now, that's the sequence of matrices, all of them elementary matrices. When we multiply them together, we expect to get A. Okay? Now, does it matter which order we multiply? Not really. Okay? So what I'm going to suggest, just to save a little bit of time and effort, is multiply these two first. Now the order matters, how you write them down, but which you do first doesn't matter. Okay? So let's multiply these two together, and multiply those two together, and then multiply the products together, and see what we get. Sound fair? Okay. So can you multiply those two? I know they're written awfully close, but you give me the product of those two. certainly going to be a 2 by 2. Okay? -1 will be the first one. Okay. Three, 1. Okay. Let's multiply these two together and see what we get. It also be a 2 by 2. 1. 2, 0, 2. Okay, let's multiply those two together and see what we get. Again, you'll get a 2 by 2. -1. So far, so good. -2. So far, so good. 3. All right, 3 out of 4, and second, 8. Look at that. That's A again, isn't it? Okay. Now, I can't think of an easier way to do this, to get the products of elementary matrices to get, okay. Do you mind if I use this word? I don't think the book uses it, but it's sort of like the same thing. These are the factors of that matrix, okay? Now, the only problem with factors, it doesn't matter what order you do. This it does, big time, okay? But these are the elementary matrices that form the factorization, you might say, of A. That's it. That is it, okay? Now, and sure enough, I wasn't checking, but -1, 0, -1, 0, 0, 1, 1, 0, 3, 1, 1, 0, 0, 2, and 1, 2, 0, 1. Gave it to us, multiplied to be that. Sure enough, there we are. Okay. Now, trying to think what that next paragraph is saying and whether I need to say it or not. All right, let's just go to the next theorem. That next couple of paragraphs, or one paragraph with a bunch of stuff in it, all well and good, but it just seemed like it was sort of another one of those sort of circular arguments. I can't tell was all that useful. But now this time I think I will write these down because these are pretty important. Okay? All right, if I erase this slide, everybody got it? Okay. Theorem 215. The reason I'm writing this down, we're building this as we go. Before we had, I think, 3 or 4, then we added another, now we're adding another. So these are equivalent conditions, and this is if A is an n by n, meaning a square matrix. The following statements are equivalent. Okay. First, A is invertible. Okay, if that's true, the next four are going to be true. Or if any of the next four are true, this is true. So these are all equivalent with each other. Now give me another word that I could have said. A is blank. Non-singular, exactly. Invertible, non-singular means the same thing. So we're not going to list that as a separate one. But just to remind you, non-singular. If it is invertible, it is singular. Okay? If it's not invertible, it is singular. Okay. Number two. Now, if that's true, number two's got to be true. But if number two's true, one's got to be true. Here's another. AX equal B has a unique solution for every n by 1 column matrix B. Okay? Because if A is invertible, we can always multiply on the left by its inverse. Okay? And if we multiply on the left by its inverse, we're going to get the identity matrix times X, and that's just going to be X. But if you multiply by the inverse matrix over here, you're going to get, it has to be a unique solution, because that A inverse is a unique matrix, multiply it by B, and you're going to get your solutions for that. So every B you write down there, if A is invertible, then this is going to give you a unique solution. Okay? So, and if that's true, that's true. Okay? Now, the third one's very similar to the second one. If A times X, vector X, is equal to the zero vector, okay, then it has only the trivial solution. Okay? Trivial solution is all zeros. Okay? Now, why is that true? Because we said this is true, it has a unique solution for every n by 1 column vector B. That includes a zero vector. And if that's true, then it has a solution, but the only solution would be the trivial solution, all zeros. Because certainly all zeros are going to work, so that's got to be the only solution. So those two, basically, there hardly could be any argument on those two. Now, here's the one we did way back. A is row equivalent to the inverse matrix of the right side, the identity matrix of the right size. Okay? I sub n. Gotta be. That's how we did it. If A was invertible, that means you can do those row operations on A at the same time doing them on I, and when you get to the end, you wind up I times the A inverse. Okay? That's how we got our A inverses, right? Our original way of doing it. So if it's A invertible, it's got to be row equivalent to the appropriate identity matrix, the n by n identity matrix. Now 5, that's the one we just come up with. A can be written as a product of elementary matrix. Okay? I'll just leave it like that. Elementary matrices. E1 times E2 times E3. There's so many, a finite number of, because you can come up, if A is row equivalent to I, every row operation you did to make it equivalent to that, come up with an elementary matrix that does the same thing, and then do the inverse of those in reverse order. That will give you A. Okay. We just showed that. Now, like I just hinted and actually said, those elementary matrices, the inverses of the the things that we did, that set of elementary matrices you could think of as factors of that invertible matrix A. If you multiply them together in the right order, you're always going to produce A. Okay? Now, we're going to talk about another factorization, you might say. And this is called the LU factorization, but we got to define what L is, what U is, okay? And actually, the one we did, I happened to back into it, making it work, but it's not always going to be the case. Would y'all mind a quick break right now? Because I am so clogged up in the head, I can hardly breathe. And I'd like to finish this without feeling so miserable about it. So let me run down, clear my head, and why don't y'all get up, stretch, do whatever it takes, and I'll put this on. All right, we're back. Any questions on what we've done so far? Now, frankly, first time I taught this, I thought, what is the point in doing all this stuff? Yeah, I can see it's true, but it doesn't make anything any easier, so why are we doing all this? I'm not sure this is a total answer, but at least it kind of smacks of being a little bit of an answer. Okay? At the heart of the most efficient and modern algorithms for solving linear systems, this is what we're dealing with. AX equal B. We keep coming back to that, and admittedly, the ones we do are so simple, you could do it a multiple number of ways. But remember some of the examples we've been talking about. When you're dealing with airlines, flight crews, routes, tying all these things together, you have literally systems of equations with thousands of equations and thousands of unknowns, okay? And it just can be mind-boggling. And yet they have to figure it out. They have to be able to get this. Google searches, or any kind of searches, okay? That's systems of equations. Huge numbers of systems of equations. So you're always trying to find some efficient, precise, shortest way to do these, because even with a Cray supercomputer, you can bog it down if you got too big a system, okay? So that's what we're trying to do, is solve something like that. At the heart of this is, to get the easiest one, is something called an LU factorization, okay? Now, if this was a regular equation, and say a quadratic or something higher, and you had some expression in x's is equal to something. If you can get that equal to 0 and factor this, then you can solve for each variable, right? I mean, for each thing, okay? X could be 7, x could be minus 3, blah, 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 okay? Well, if we could factor that matrix A, which is not an easy thing to do, okay? That's why I pointed out those elementary matrices were indeed bunches of little factors of it. But if we could come up with one factor that could make this whole thing much easier, what L is what they call a lower triangular matrix. And what U is an upper triangular matrix. Okay? And if you can find a factorization for that matrix A with an upper and a lower triangular matrix, then you are going to have a much easier time solving that equation. And you almost just have to take my word for that. So what do we mean by a lower triangular matrix? One that looks like this. We're going to deal with a 3 by 3 because they're simple, they're easy to write. A1, 1, but 0, 0. A2, 1, A2, 2, 0. A3, 1, A3, 2, A3, 3. Okay? That's a lower triangular matrix because below all the components below the diagonal are components, all the ones above are zeros. Okay? If this was a 7 by 7, then everything up there would be zeros. Everything. Things down here would have values. Now, some of these may be zeros. That's okay. It's perfectly all right. But they all have some values. These have to be zeros. And anyone want to hazard a guess what an upper triangular matrix would look like? 3 by 3, A11, A12, A13, 0, A22, A23, 0, 0, A33. That, sure enough, is an upper triangular matrix. The diagonal and above all have values. Below the diagonal, all zeros. All zeros. Okay. So, here's what we're saying. Now, A, remember, is an n by n matrix. Square matrix. Okay? If A can be written, so if the square matrix A can be written, okay, as a product of a lower triangular matrix, L, and an upper triangular matrix, U, then A is equal to LU, that product is an LU, then A equal LU is the LU factorization. So, I mean, this definition almost is circular, okay? It can be written as a product, it's a factorization, okay? So if you can do that, if you can split that A into a product of a lower triangular matrix and an upper triangular matrix, then, and the product of them equal A, then it's a LU factorable, okay? Now, to begin with, all we're going to do is show some LU factorizations. Not how to get them, just show what they are, that they are, okay? So, here's a matrix. 1, 2, 1, 0. Okay. Now, they're saying to us 1, 0, 1, 1 times 1, 2, 0, minus 2. First, what kind of matrix is this? There. It's a square, 2 by 2. Anything else special?
Lower.
It's a lower triangular, and this is an upper triangle. Okay? So, here's a lower triangle multiplied by an upper triangle. Let's see if that produces this. Okay?
That's 1, 0,
1. Okay, we're okay there.
2,
2. Okay, so far so good.
1, 0,
Okay? And
2,
so sure enough, this is a lower triangular matrix multiplied by an upper triangular matrix, producing that matrix. So this matrix has an LU factorization. A lower times an upper, you can factor that matrix into that. Okay. Yay. Amazing. So what? I mean, okay. We know it works. Okay? Now, here's another. Here's a matrix A, bigger one. 1, -3, 0, 0, 1, 3, and 2, -10, 2. Okay. Now, making a statement here, I don't know if we want to buy it or not, but here's what they're saying. This is 1, 0, 0, 0, 1, 0, and 2, -4, 1. And here's another. 1, -3, 0, 0, 1, 3, and 0, 0, 14. Okay? Now, first tell me, what is this?
lower triangle.
Lower triangular matrix?
Upper
Upper triangular matrix. Well, they say these multiply. Let's check and see.
1.
That's a 1. So we're okay so far. Guess what? It's just going to reproduce this row. Go on there, get 3, 0. That's fine. And guess what? This is going to reproduce that row. You buy that? Okay? So let's see about that third row.
2, 0, 0.
Wait, I did the wrong one. Sorry. 2, 0, 0. That gives you 2. I'm sorry. I did the wrong one. Okay? So the first entry is fine. The 3, 2 entry,
-6.
-6.
-4.
That'd be -10.
0.
-10. One more.
0. -12. So it's 2.
Oh, positive. -12 plus 14. Yep. This matrix A does factor into an upper and a lower triangular matrix. So what? Okay. All right. It does. We'll buy it. Where are you going? Okay. Now, before I move on, there's a little blurb at the bottom of the page. I don't know what type of engineering you are, but do you think any of you are in a field that you would deal with fluid flow, fluid dynamics? I would think mechanical engineers certainly will. Have you already hit some of that? Okay, but there's almost a certain, yeah, fixing to, okay? Linear algebra, all over it, okay? The computational fluid dynamics, there's a little blurb on that. Aerospace companies like Boeing and Airbus have used computational fluid dynamics analysis in aircraft design. In fact, nowadays, they don't build planes and check to see if they work. They do little bitty models in air chambers and other things like this, they test everything out and scale down things before they ever go to the victims, okay? And they're almost certain, almost being the operative word, that everything's going to work before they invest in building a victim, because they do things such as this, which is all over with linear algebra. Okay. So, a little bit of a rehash here. If a square matrix A row reduces to an upper triangular matrix U using only the row operations of adding a multiple of one row to another row below it, then it is relatively easy to find the LU factorization. So you say, okay? All you need to do is keep track of the individual row operations as shown in the following examples, okay? So here's what we're going to do. Now, these can get, there are so many multiple steps here, you have to basically almost keep them in order and keep them right, but then they're doable, okay? It says find the LU factorization of this matrix A. Here's A. 1, negative 3, 0, 0, 1, 3, and 2, negative 10, 2. Okay? All right. Now, not putting aside LU factorizations and everything else, what if I gave you this matrix and said, work on it, okay? What would be the first thing that came to mind to want it to happen? Second? In row echelon form. Now, not reduced, just row echelon form. And what would be the first thing you would do? Right, okay. You got a 1 in the upper left, that's exactly what you want. You got a 0 below it, that's exactly what you want. And then you've got a 2 that you want to become a 0, so we'll do that. And what did you say it was again? Negative 2 row 1 plus row 3. Okay? And that would produce, okay. Now, it says keep up with what you're doing. Okay? So that means one way of keeping up is writing the elementary matrix that does that. Okay? So we're going to be doing this over here on the side too. Okay? So this produces, first row stays the same, 1, negative 3, 0. Second row stays the same because it already had a 0 where you wanted it to. And what's the new third row? 0. Negative 4. 2. Okay. What was the elementary matrix that made that happen? It would have made that happen if you used it. 1, 0, 0, 0, 1, 0, negative 2, 0, 1. You got it. You got it. Okay. Now, while we're here, let's go on and come up with the inverse for that matrix. And what would that be? No, we didn't mess with the first two rows. 1, 0, 0, 0, 1, 0. That didn't change. It's only that third row. It's what? 2, 0, 1. Okay, remember? When you do a multiple of one row by another in the elementary matrix, do the opposite multiple to the same row. Yep. Of the other. Yep. That's it. What's that? What's that?
So you don't change the 1 to the main diagonal, just the 2.
Yeah, you only do one operation. And that's the 1. Yeah. Multiply them. See if you get a identity matrix. I think you will. Okay? Now, what's the next thing we want to happen? Yeah. You got a 1 here, 0 below it. You got a leading 1 here. You want a 0 below it. This is just row echelon form, not reduced. Row echelon form. So how will you make that become a 0? How will you make that become a 0? Second? 4 times row 2 plus row 3. Got it. Okay? And what will you get then? 1, negative 3, 0. That doesn't change. 0, 1, 3. That doesn't change. Help me, help me. 0, 0. 14. All right. Now, what elementary matrix would have done the same thing? 1, 0, 0. Nothing changed there. 0, 1, 0. Nothing changed there. 4, 0. No, 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 no. I don't think so. Row 2, not row 1. Yeah. Okay. Second? Yes. 0, 4, 1. Ah, good. And what would have been its inverse? Okay, and the last row, 0 minus 4, 1, and the other two stay the same. All right. Okay. Got it. Guess what this is? Yeah, it's a lower triangular matrix. That's what we have always been producing, we just haven't said it. When you do row reduction, you get a lower triangular matrix. Okay? Now, so we got one. All right. Those are the steps it took to get there. Okay. Now, I do want to go back up and re-emphasize something. That paragraph at the top of that page. If a square matrix A row reduces to an upper triangular matrix, which is what we got here, right? Did I say lower before? That's upper, because all the numbers are in the upper part, upper triangular matrix, okay? Upper triangular matrix, U, using only the row operation of adding a multiple of one row to another row. That's what we used. We didn't flip 2 rows, we didn't multiply by a constant. We only did the third one, which is a multiple of 1 by another, added to another. As long as you can do that and get to this form only using that step, that row operation, and produce an upper triangle, you're okay. Okay. So we did that. Okay? So, would you agree with this? We started with matrix A, right? Everybody agree? Now, we did row reduction because it was easy. But if we could have done the same thing by multiplying first by E1 and then by E2, that would have given us this upper triangular matrix, right? That's what we did, but we could have, we did it with row reduction, but we could have done it using the elementary matrices. You buy that, okay? Now, that reduced matrix U, upper triangular, you got this, okay? Now, what if, would you also buy this? If you had multiplied this, were to multiply this by E2 inverse, and let me, again, I didn't plan ahead, put the U over here, and then multiply this by E2 inverse, right? That would be the same thing, right? Okay. then multiply, and this becomes the I matrix, so you could basically discard it. And then you multiply this, the result, by E1 inverse. E1 inverse. Got to do the same thing to both sides, right? Then this produces the I matrix, right? Okay, that, okay. And then you have some new matrix here multiplied by U. These are I's, and that gives you A, right? Because these are just I's here. You would get A over here by itself, and this would be this some new matrix here times U. Well, guess what? If this product here turns out being a lower triangular matrix, we've just done it, right? So let's see if it does. And you have to do it in the right order. That would be 1, 0, 0, 0, 1, 0, 2, 0, 1. Multiply that by 1, 0, 0, 0, 1, 0, 0 minus 4, 1. Let's see what happens when you multiply. Now, do any one of you want to hazard a guess that you might not get a lower triangle out of this? Because these are just basically going to reproduce themselves here, aren't they? Only the bottom row is going to be 10. So I think we can almost guarantee that's going to be a lower triangle. Let's see if it is. Can you do the multiplication? It's going to be the first entry, which is 1. The 1, 2 entry, exactly. And the next one, 0. Okay. The 2, 1 entry, 1, 0. And the 3, 1 entry. Height. No, never mind. Okay. What does it come out being? Really? The 3, 1 entry.
Oh, sorry.
Right? What does that give you? 2. Okay. Next, 3, 2 entry. -4 and 1. All right, let's see if that's what they got in the book, because that seemed way too easy. 1, 0, 0, 0, 1, 0, 2, -4, 1. Yep, and that is indeed a lower triangular, and it sure should work that we multiply it by our upper triangular here. We should reproduce A. Now, there's no guarantee that's going to work. You want to try it and see if it does? That's about all we have time left to do. So if it's okay, I'm going to erase E1 and E1 inverse. I hope I won't need them again. And let's multiply those two together and see what we get. We have to do lower times upper, LU. Okay, this is lower. This is upper. Where's upper? There's upper. Okay? So 1, 0, 0, 0, 1, 0, 2, -4, 1 times 1, -3, 0, 0, 1, 3, 0, 0, 14. Can you multiply those two? The answer is sure. What size? 3 by 3. Socket to it. 1. 1, 2. -3. Okay. And 1, 3. 0. Okay. 2, 1. 0. I went too soon, didn't I? Okay. She's making fun of my writing, I can tell. Okay. That's a 0.
Oh, okay. 0, 1, 0.
Okay. You buy my 1 then. Okay. Next. 2, 3. 3. Okay. And so far, so good. And then the 3, 1 entry. Two. 3, 2. -10. And 3, 3. Second. 0. -12. +14. 2. Ding, 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 ding. That is the A. Okay? And sure enough, we had a lower time and upper that gave you that. Okay? Now, again, let's see how we did it. Simply row reduce A. Just like we always have. Get it in row echelon form. Not reduce row echelon form, row echelon form. But this is where the elementary matrices come in. Track those elementary matrices and do the same process you did here. Okay? And at the same time, go on and get their inverses, which is pretty simple to do. Now, if all those elementary matrices are only the ones that are multiplying one by adding a multiple of one row to another, if you can do that, then you're fasted. You're perfectly fine. Get this in row echelon form, not reduced row echelon form, row echelon form. That gives you an upper triangular matrix. Take those inverses and be sure you do them in reverse order. E inverse 1 times E inverse 2 from the left rather than the other way. Okay? And multiply those. And you might have had 17 of those together. However many you had, we only had 2 here because we had that in really good shape to begin with. Then when you get that result, multiply those 2 together, that gives you a lower triangular matrix. You got it. Then you have an LU factorization. Okay. All right. So here again, here's a statement. Now I know we're out of time. If a row reduces to an upper triangular matrix U using only the row operation of adding a multiple of one row to another row, then it has an LU factorization because you can go backwards and do it. Okay? If you had to do something else, like multiply one row by another or switch 2 rows, no, it's not going to work. Okay? If you can do it using just that one operation. Okay? Now, once you've obtained the LU factorization of matrix A, you can then solve the system of n linear equations with n variables of AX equal B very efficiently in 2 steps. we'll pick up and do that next time. Okay, so that's going to be what we do with example 6. Okay, now your test is going to have you do that last thing we haven't done yet. But up to then, that's, I think, just the last problem or 2 problems. If you want to go on and get your test now so you can work over it on the 4th of July, which sounds like a fun thing to do, you can. Or if you'd rather wait until Thursday, I'll definitely be giving it to you on Thursday. You like it now? Okay. Let me go on and pass it out to you now. We haven't done the last part of that, but the up until that we have done. So here's test 2, and I think you've done everything on here down to, actually we have done it. All it said is find the LU factorization of a matrix. It didn't say work with it. So actually you've done everything on here, so you can do it all. Okay. You can have it all. No. I didn't send the other guy. All right, good deal. Have a great 4th of July. I mean, too much barbecue, but eat plenty. Okay. Have fun. We'll see you Thursday. All right.
Do you have a test in differentials?
I'm sorry?
Do you have a test in differentials?
For a differential equation? Not quite. Well, wait. Nobody was here, so I know I didn't pass one out.
Okay.
We came, actually we were awfully close. I have it made out. I just don't remember if we're far enough along. Thursday I'll give it to you. Okay. I don't have it up here now. I'd give it to you now, but I took it through my office. Bye-bye. Have a good week.